Anyway, let's start with a quote from my spectroscopic hero, who's a chap called William Huggins. You may have heard of him, a Victorian gentleman astronomer, as most astronomers were during the 19th century. And he wrote this comment towards the end of his life, maybe 10 or 15 years before he died. And he wrote an essay, I've got a copy of it, which he called The New Astronomy, when he kind of looked back across his spectroscopic career. And I thought he wrote this beautiful little piece trying to sort of get across the poetry, the beauty of spectroscopy. And he wrote, I'll read it. The only known communication from the stars which reaches us across the gulf of space is the light which tells us of their existence. Fortunately, this light is not so simple in its nature as it seems to be to the unaided eye. In reality, it is like a cable of many strands. Let this light cable pass from air obliquely through a piece of glass, and its separate strand rays all divide. Within this unraveled starlight exists a strange cryptography. Some of the rays may be blotted out, others may be enhanced in brilliancy, and these differences form a code of signals. And it was the discovery of this code of signals and of its interpretation which made possible the rise of the new astronomy. And that end sounds very grand, but of course, as I'll mention later, you know, spectroscopy is a huge pillar, critical pillar of professional astronomy. Without it, we'd know so much less. We'd basically be relying on changes in brightness and position of stars and so on to learn more about the universe around us. Spectroscopy is really what delivers us, in many ways, the detailed information that we have about the universe around us. So, yep, my sort of introductory slide, and there's a portrait of William Huggins which hangs in Burlington House, which of course is the headquarters of the Royal Astronomical Society in London. And I took this photo. I was there for a British Astronomical Association meeting, and I sort of sneaked off, and I sneaked to the top of the staircase. I don't know if you were allowed up there, but I went up there, and his portrait's right there at the top, one side of a doorway. And I guess this is him again, probably around the time he wrote that quote that I just read out to you. And on the other side of the doorway is another portrait, and you'll learn about that portrait later in my talk. So yeah, this is introduction about me, but I think you've covered it pretty well, Chris. You know, I am chairman of the Wells and Mendip Astronomers down here in Somerset. It's raining here just like it is up in Hereford. It has been for the last couple of days. Definitely no astronomy around here for the last few days. There's Wells Cathedral. I think Hereford has an equally beautiful cathedral, I believe. I've never been to Hereford though, so I would like to come. And Chris, if I do come back, I'd come in person to talk to you, and then see Hereford at the same time. Here's me observing during one of our monthly meetings on the village green where I used to live, actually, in Oak Hill, which is a little village 5 miles outside Wells, just up in the Mendips. So we kind of meet all over the Mendips. It's quite a dark sky. Sounds like it's a similar kind of dark sky to areas around Hereford as well. I don't just do astronomy. I play a lot of badminton, and I'm actually serving here to my wife. I can't remember who won the rally because she's a pretty good badminton player, to be honest. And as you mentioned, Chris, I'm an industrial chemist, and I spent my career in the printing ink industry in the last 20 or so years in the formulation of inks for industrial inkjet printers. And that's probably where I got the engagement I have now with spectroscopy. Actually, when I started astronomy, I was always fascinated by spectroscopy. And as I learned, as I got into the amateur astronomy world, that amateur spectroscopy was a real thing. I knew that one day I'd be doing this. So I actually bought my Alpi spectroscope, and shortly afterwards my star analyzer that you'll see me talk about in a minute. I bought them probably about 7 or 8 years ago now. So I've been doing spectroscopy for a little while. So here's just a presentation of some of the spectra I've taken over the last couple of years. I can't remember the star, the photo I took of the star here in the middle. I think it may be Capella. But anyway, this is just a way of sort of communicating, I hope in quite an eye-catching way, the variety of spectra that you can capture. And you sort of see, first of all, I suppose, what catches your eye is the rainbow of light that underlies, well, I was going to say all, but that's not true. Actually, this one has no rainbow of light, and we'll sort of touch on that later. But all the others do. And what you see as well is the sort of position of maximum brightness of that rainbow varies between these different spectra. So in some of them, it peaks way off in the red or near infrared even. And in some of them, it peaks in the violet and in the near UV. And some it's sort of relatively evenly spaced. So this spectrum here, for example, is similar in many ways to our sun. So that's one of the first things that catches your eye. And then, of course, you see that the spectra are full of features, as I call them. So some of these features are dark lines, absorption lines, and some of them are bright lines, emission lines. And these also have a great story to tell. So there's a lot of information in these spectra, but I think there's also a lot of beauty. So what we're going to see, you're going to learn from this, are things like the temperature of the body you're looking at. You know, I mentioned when we were just looking there at that spectrum of Antares, you know, we know, don't we, orange, red stars are cool stars, blue stars are hot stars, and there is this sort of emphasis in the brightness demonstrated in these spectra. Chemical composition, of course, and that's, I suppose, my entry point into spectroscopy as a chemist. You know, these features, these absorption lines and emission lines, they're like fingerprints, and they're fingerprints of chemical elements and molecules as well. And of course, by interpreting these features, as William Huggins said, we can also begin to look at things like motion of these objects, Doppler shift of these features in the spectrum. And of course, we're particularly interested, aren't we, all of us, when we look at the sky, change, you know, what's changing up there? Things moving, changing in brightness. Are there changes in spectra, and what do they mean? And I'll finish my talk by touching on the search for life. I mean, I honestly believe that spectroscopy may be the technique that detects the first signs of life on another planet. And I know, of course, we're looking for signs of life in the solar system, and maybe we will find them. Maybe Mars won't turn out to have been, well, it certainly is now, but to always have been a rather inhospitable place. And maybe we'll find signs of life under these frozen surfaces of the moons of Saturn and Jupiter. I don't know, but I think with the telescopes and spectroscopic techniques that are emerging now, we may well be able to detect signs of life by spectroscopy, and I'll touch on that at the end. And of course, I do hope that there will be some fun in this. I mean, there's going to be a lot of technical stuff. I'm sorry for that. Well, I'm not too sorry for that, because I hope some of you will have an experience that will sort of pick up different parts of the technical stuff, understand it. Don't worry if you don't understand it all. Let it wash over you and just enjoy the bits that you do enjoy. But honestly, spectroscopy is fun. Even if it's difficult to say the word. It's funny, you know, I gave a talk to a couple of years ago now, just before the pandemic, I think, and I put the word spectroscopy in the title. It was a talk to a local science society. And I got an email back when I proposed the talk that said, yeah, great, sounds really interesting, Hugh, but could you take the word spectroscopy out of the title, because no one can say it, which I thought was quite funny, but there you go. So look, here's another quote from William Huggins in this essay he wrote. Spectrum analysis could not fail to have a powerful influence on the future of astronomy. And of course, he was absolutely right. Unfortunately, and I've titled this slide, Amateur Spectroscopy Clouded Out, a bit like the weather at the moment. You know, I kind of, as I got into spectroscopy, I began to realize that it's like such a niche thing within the amateur world, and it really shouldn't be. And you know, you go into popular magazines, and I take Astronomy Now, but you know, I've also had subscription to Sky at Night and so on, and there's very little mention of amateur spectroscopy in these magazines, very little. I'm not quite sure why. Maybe it's because it's felt it's too technical, astrophysical, whatever. So I bumped into Keith Cooper, the editor of Astronomy Now, at one of the Astrofests in London a few years ago now. And I said, look, shall I write an article for you for Astronomy Now? And I wrote this article. And it was based really around this talk that I give, that I've given a few times now, just to try and get across the interest, the excitement, and some of the background to amateur spectroscopy. So I begin this talk always just asking this question: what does spectroscopy mean to you? And I'll ask it at the end, and I'll give some different answers. and hopefully you'll agree with them, but maybe at the moment, it perhaps represents obscure language, complex techniques, blaze, diffraction grating, dispersion, response correction, equivalent width. What on earth does all that mean? And I'm not going to pretend that I can answer these questions for you sufficiently now, but I hope to demystify a little bit some of the language and techniques of spectroscopy. And of course, you can think about the physics of spectroscopy, how the wavelengths that are emitted or absorbed are generated, and how diffraction gratings work to generate spectra, and what's the resolution of spectroscopes, and how do you calculate the velocity of an object from the Doppler shift. And you can do all these things and get into them depending on what your particular interest is, but you can get a lot from spectroscopy without having a deep understanding of astrophysics, I can assure you. And look, I'm a chemist, I'm not a physicist, and I love it. Of course, it may just mean a painful medical examination to you. That word oscopy at the end, my goodness, what on earth is this all about? Well, I assure you, hopefully this isn't painful. I don't know about you, but I like to think about the history of a subject. I find that enriches the subject and helps sort of bring it home and bring it to life. And so I'm going to start with a few slides about the history of spectroscopy. Start with a question, actually. I mean, hey, we're all familiar with the sun spectrum, aren't we? Surely. Rainbows, we see them a lot, certainly in this country. Here a few years ago now, I was waiting outside Bristol Airport for my wife coming back from a trip. And there was this beautiful double rainbow that I took through the car windscreen. And of course, that famous album cover on the Pink Floyd album, Dark Side of the Moon, the formation of a spectrum by refraction of white light through a prism. And I actually prefer the beer bottle version. And then, of course, and many people perhaps don't realize it's that different technique for producing a spectrum, but we see a spectrum formed by reflection off the surface of in this case, a DVD. And this, of course, is diffraction rather than refraction, and we'll talk about that. And of course, we know that it was Isaac Newton in 1666 or 7 who sort of developed an understanding of the spectrum and understood how white light could be decomposed into a spectrum and then recomposed again into white light. And his brilliance, his genius, led to this understanding and sort of, if you like, set us on the road to spectroscopy. But there's one theme that connects all these pictures, and I would say we are not familiar with the sun spectrum, or as familiar as we think, because what we don't see in any of these spectra or in Newton's paper from 1667 is the features inside the spectrum. They're completely lost, and they're lost because the sun is a big object, so light's coming from one side, overlapping with light from another, from the middle, and that essentially blurs out all of these features when you put the light through a spectrum. You've got many overlapping spectra, in fact. And the way to focus that light is to put the light through a tiny thin slit, and then suddenly all these features become visible. And it was nearly another 150 years before this was done in a really very high quality and precise way. There's some speculation as to why Newton didn't see these features. I mean, he did let the sunlight pass through, as he called it, a crevice in the window of his rooms at Cambridge. But clearly that crevice was large. And maybe also it was the quality of the glass he used to make the prism he was using. And that's the link really to Fraunhofer. I mean, again, I'm sure you've heard of Joseph Fraunhofer, and he was actually an expert glassmaker, and he was interested in the spectrum formed by prisms made from his glass in order to use it as a way of assessing the quality of the glass, the quality of the spectrum that the sunlight produced. Gave him a good measure of the quality of the glass. And this is his description of, if you like, how he produced the spectrum. And you can see that he's passing the light through a very narrow opening, as he calls it, or a slit. I mean, he gives the width in arc seconds, so an angular width, but you can, with the dimensions he quotes, you can convert that into a sort of a length dimension. And it's about 0.5 millimeter if you work it out, about 500 microns. So it's a pretty narrow slit. And when he did that, and this is his drawing of the sun spectrum, and apart from the exquisite beauty you see in there of the absorption lines that he's able to see in the spectrum, and he shone the light through a little telescope, by the way, so he could really focus in on these individual lines. He produced this beautiful drawing. This is from his original paper. And note that on the left-hand edge, so the least refracted light, it's red, and it goes all the way through to the blue-violet end here. You know, obviously the sort of limits of human vision, the sensitivity to the color here starts to fade away. And he noted, I think, something like 500 absorption lines, dark absorption lines in the spectrum. And of course, the strongest lines are still called the Fraunhofer lines in the sun spectrum. What I love as well is he actually drew a graph, you know, and you'll see a lot of graphs. And I mean, I'm a graph person. Maybe you are, maybe you're not. But I'm afraid if you do spectroscopy, you have to get used to graphs. But once you get used to them, you can interpret them so quickly, and of course you can actually see more in a graph than you can visually. You know, the contrast starts to weaken a lot as you get to faint lines, but you can pick them out when you draw a graph of intensity against wavelength. But that's essentially what he's done here. He's drawn a graph of that rainbow intensity that we spoke about at the beginning, and you know, seen that the intensity of the sunlight rainbow is somewhere in the kind of blue-green area of the spectrum. So I think that's beautiful. What a drawing. And the thing with Fraunhofer, he did actually then try and apply this technique to astronomy. And he wrote this paper in 1823. And maybe it wasn't so widely read because it was published, perhaps what was then an obscure journal, the Edinburgh Philosophical Journal. But he wrote, by pointing his telescope and with a prism at stars, he said, I have seen with certainty in the spectrum of Sirius 3 broad bands which appear to have no connection with those of sunlight. One of these bands is in the green, 2 are in the blue. And he added that he hoped to induce perhaps some skilled investigator to continue the experiments. I mean, he wasn't an astronomer, he was a glassmaker, but very inquisitive, intelligent guy. So he did this work, and unfortunately nobody took him up. So here we are 150 years after Newton, if you like, understood a spectrum for the first time, and we've still not really exposed the true richness inside the spectrum. So after Fraunhofer, here are some just sort of milestones I like to pick out in the history of spectroscopy. So it was another, 50 years after Fraunhofer in 1814 before the first pioneers of astronomical spectroscopy emerged. So I've mentioned William Huggins. There was also Angelo Secchi, an Italian Jesuit priest. There was a chap called Lewis Rutherford working in the US. And this is the birth of what Huggins called the new astronomy, the mid-1860s. Another critical milestone for spectroscopy was the development of photography in the 1870s, particularly Henry Draper. And of course, this is the way you can actually capture a spectrum. You know, those 1860s pioneers, they just observed the spectrum through little telescopes. You know, other than sketching, they had no way of recording and then analyzing later and in more detail what they saw at the telescope. So photography, the development of photography was crucial to the development of spectroscopy. And in the 1920s, this idea of blazed diffraction grating emerged, and I'll explain a bit more about that in a minute. But this was crucial to the gradual transition of spectroscopy from a technique based on prisms to a technique based on diffraction gratings. And then, of course, if I don't know how many of your members, Chris, do astrophotography, but you know, if you do astrophotography, you'll almost certainly be using, or will have used, a CCD camera, or I guess now increasingly a CMOS camera, but basically an electronic detection.
We have quite a few. We have a couple. Yeah.
Yeah, great. So
some very, very impressive.
Yeah. So CCDs, of course, again, it's a technique to capture an image, but of course it's incredibly sensitive. So you can do very long exposures and really capture very, very faint objects. And this is crucial in spectroscopy. So here's just a reminder, if you're not sure already, about the difference between refraction and diffraction. So on the left here, I've put refraction. So all of the light in the spectrum, the white light in the spectrum, is all of the white light refracted through the prism goes into one single spectrum. And as I mentioned, the red is the least refracted, the blue is the most diffracted. And I don't know if you noticed, and I forgot to point it out, in that hand drawing of Fraunhofer's, you see the extreme non-linearity of a refracted spectrum. So the red end is really compressed, bunched up, and then as you go out from green to blue, the green-blue area of the spectrum actually takes up probably 2/3 of the width of the spectrum. So it's very non-linear. So it meant that the technique was very good for picking lines out in this area, the green-blue area, but not so good in the red area. And of course, glass has other problems. It absorbs UV and infrared. So maybe if your interest is in the near infrared and the near UV, you know, you have problems if you use glass. So there are reasons why diffraction grating is more interesting, because here's a diffraction spectrum. So the light comes through the grating here. Some of it goes straight through. Actually, quite a lot of it just goes straight through and forms what we call the zero order image. So if you shine light through a diffraction grating, you can actually see, if you like, what's the other side. But it then also forms a spectrum on either side of the zero order. In fact, it forms multiple spectra. I've just shown you the first two, what are called the two first order spectra. But there's another one, and another one each side. And in fact, they start to overlap very quickly. So you can imagine now this, in a way, you could see this as quite a wasteful technique. You know, some of the light goes straight through, some of the light gets put into a lot of different spectra. They get increasingly faint as they spread out. That's why you need these sensitive cameras, because you're spreading, you're taking this, what I call, I say at this point at the end here, this blob of butter, and you're spreading it really thinly, and it thinner and thinner and thinner. This is the importance of this technique, blazing, because all blazing is a way of physically changing the physical form of the lines, the grooves that make up a diffraction grating, so that it pushes as much of the light as possible into just this order here on the right hand side. So you still get all of these other orders formed at the same time, but with blazing and understanding of how to physically orient these grooves in the diffraction grating, you push as much light as possible into just this first order. And if I was with you, I actually have a little red light, you know, an LED pointer, which is just a laser light, so it's almost like a single wavelength. And you see very nicely the multiple red dots produced by the diffraction grating, but one of them is much, much brighter than any of the others. So once blazing was developed, it became realistic, practical to use diffraction gratings rather than prisms. So here are my two spectroscopes. This on the left here is a complete spectroscope. This is the star analyzer from Peyton Hawksley. It comes in two rulings, two gratings, if you like, 100 lines or grooves per millimeter, or 200 lines per millimeter. And the more rulings there are, the more finely spaced rulings there are, the more the light is spread out. So the thinner the blob of butter is spread. And this is so easy to use. You know, if you do astrophotography, you've probably used filters on your camera. Well, this just replaces where you put the filter. It's deliberately been mounted in a 1¼ inch thread-on a ring, just like a colored filter, and you just thread it onto the nose piece of your camera, and you're ready to do spectroscopy. And it costs about 100, 110 pounds. This is just one tiny piece of the other spectroscope I use, and to be honest, the spectroscope I use most. It's called an Alpi spectroscope from a company in France called Cheliac. They make many different models of spectroscope. This is just the slit, and this is what I wanted to show you. Maybe if I zoom in using my zoom, there you go. You can probably see that a bit better, and you can just see the slit there. So it's etched into a mirrored piece of glass. So the glass has a mirror coating, and there's a tiny 23 micron wide groove. It's about 3 millimeters long, cut into that mirrored surface, and that is the slit. And it's the narrowness of that slit that brings out the features in the spectrum. So you might say, well, how does the analyzer work if there's no slit? Well, the analyzer relies on the tiny size of stars in the sky. So provided you're doing spectrum of stars, you can use a star analyzer because the tiny size of the spot of light, if you like, acts like a slit. So how much will an Alpi cost you? Well, it comes in 3 different modules, and if you buy all 3 modules, that will cost you probably, well, what with inflation now and everything, it's probably 1,700–1,800 pounds. Now, you may gasp at that. I would argue, if you're serious about a hobby, 1,800 is, if you like, a reasonable amount for a tool that you'll see is so extremely capable. I'm not saying it's a trivial amount of money at all, but I think, you know, in the broad scheme of things, it's a very, very good investment. So here, what I call slitless simplicity. So this is the star analyzer. My star analyzer just threaded onto the nose piece of my astronomical camera. This is an Attic 314L camera from Attic Cameras. Absolutely superb camera. Actually, I think they've just become obsolete. It's a cooled camera, so it allows you to take very long exposures. And you can just see the chip of the camera here. And you orient that the grating in very specifically. There's actually a little white line on the ring of the grating, so that, as you'll see, the spectrum is then cast horizontally across the chip. And here's an example of an image straight out of my camera that I took a few years ago. This is that beautiful summer binary star, Albireo. So, you know, the brighter component is a beautiful gold color. The fainter component is blue, and you get this wonderful color contrast visually in a telescope. And if you haven't seen Albireo in a telescope, I absolutely recommend you do. It's stunningly beautiful. You may even just catch it now. I mean, then the Cygnus is probably setting a bit now into the dusk, especially as the day length increases. I think you'll have to wait now until you get back into the summer. And here's a much fainter object. Here I was taking the spectrum of the brightest quasar in the sky, which is just this object here. Can you see how every object in the field of view, by the way, casts a spectrum with an analyzer like this? And here's the 0 order image, if you like, of each star. And then each star casts a spectrum out to the right. And the left-hand end of the spectrum is the blue-violet end, and the right hand is the red end. So much longer exposure, 105 seconds. Here's the quasar spectrum. Here's the actual quasar itself. And you can just see a bright emission line there, which is hydrogen. Massively redshifted from where it should be because of the distance of this quasar from us, about 2.5 billion light years. And there's plenty of help out there to use a star analyzer. You can go online onto the website of the chap who wrote a bit of software for processing spectra, called RSpec, Tom Field, and he wrote a little sort of table that you fill in with the spec of your system, you know, your telescope, your camera, and so on, and he tells you whether the position of your star analyzer is good or whether you need to adjust it. But if you're going to do spectroscopy with a star analyzer, I would say 3 pieces of advice. Always put the spectrum horizontal, as I mentioned. So your stars are here over on the left-hand side of the camera view, and they cast the spectrum to the right. So you orient your star analyzer so that the spectrum is thrown out horizontally. So it's thrown out along the line of pixels on the CCD sensor. focus on the spectrum, not on the zero order image of the star. So I don't know if any of you use a Batinov mask, but if you get this nice symmetrical pattern when you put the mask over the front of your telescope, it means your telescope's in focus. So here I've focused the telescope perfectly on the zero order image of the star, and the line, this is just a zoomed in image of one of the absorption lines in the star I was looking at. I think it was Vega. You can see it's quite blurred. You see it's got a very strange shape to it and it's blurry. If I defocus the zero order image slightly, I get a nice sharp absorption line. And then thirdly, don't overexpose. This is a common problem. People forget, you know, they take too long an exposure, they overexpose, they don't notice, and then they get a warped spectrum. So keep an eye on the exposure in your camera and keep it below saturation. So here's the picture of my Alpi spectroscope on the back of my telescope. These are the three modules, this one, and this one. And I have two cameras. I have these, what I guess you'd call the science camera, my attic, that's actually taking the image of the spectrum. And this is my guide camera, because obviously what you can't do is look through the telescope to see where you're pointing it. So the slit, remember, is actually cut into a mirror. So the mirror is angled like this. So the light comes through here, and obviously some of it goes through the slit into the spectroscope itself, which is here, the diffraction grating, and then the spectrum is cast onto the camera. The rest of the light gets reflected off the mirror, and that's what the guide camera is looking at. So it's quite a clever idea, isn't it? So I guide my telescope, I manually guide, because mine is a fork-mounted telescope. I guide my telescope using the continuous image that's being streamed, if you like, from this camera. And as I say, this whole setup, excluding the cameras, would probably be about £1,700 or £1,800 now. And this is the spectrum you get of sunlight. Actually, you don't need a telescope to take this. You just take the whole spectroscope off the back of the telescope, point it at a cloud, not directly at the sun, point it at a cloud, and there's the spectrum of sunlight. And because you're using a very narrow slit, it doesn't matter how big the sky is, as it were, you just get this very narrow line of light that is projected onto the diffraction grating, and you get a beautifully resolved spectrum. Notice, of course, that it's violet on the left, whereas Fraunhofer, using a prism, had violet on the right. And here's the spectrum you get from a star. Obviously, a star is a point of light, more or less. So it's very narrow now. It's just filling a tiny part of the slit, and you get this lovely narrow line of light. You can probably just about see, maybe if I zoom in a bit. Can you see features in this spectrum? So this is the blue-violet end here. You see these dark absorption lines, and then some more features here in the red and near infrared. So what do you get for this sort of, you know, £1,700 difference in these two spectroscopes? Well, this is my star analyzer spectrum of Vega. This is my Alpi spectrum. And can you see how much sharper the Alpi spectrum is? So this is, if you like, a visual way of getting across to you what's meant by resolution. So what Alpi gives you is a significantly higher resolution than the star analyzer, and you can pick out more features, especially the lower contrast features here in the spectrum. They're really lost in the star analyzer spectrum. Now, like all these sort of new techniques, there is a learning curve, and it's a steep learning curve in places. But you know, if you persevere, you get to the top, don't you? I'm not sure you ever get to the top, but you get to a nice high vantage point from which you can do a lot of interesting stuff. And one of the things you have to do is learn about software, and that's basically how to take your astrophotograph, if you like, your picture of the spectrum, and turn it into that kind of graph and resynthesized spectrum that I showed you at the beginning. In other words, the kind of color spectrum. And of course, once you've turned the picture of the spectrum into numbers, so you can plot a graph, you can actually do science and detective work with it. So that's the idea really of these pieces of software. Most of them are free. ISIS, BAS, and Demetra are all free. This one, RSpec, I mentioned already, written by this chap in the US called Tom Field, he actually charges for his software. I think he's probably right to, because what he's done is he's actually a programmer, I think, by profession, and he's put a lot of time and effort into making it really, really intuitive, and he's got a lot of videos. So a lot of people begin their spectroscopic journey with RSpec software, and then the capability is probably a bit more limited than these other bits of software. I use BAS now. I started with RSpec, but I've migrated to this software called BAS. And this is what you can produce. So this is the spectrum of another star similar in temperature to Vega, called Alioth. And this is its spectrum. So you can see those dark absorption lines as these lovely, beautiful, sharp dips. So these were the dark lines we saw in that photograph of the spectrum from my camera. So when you process it in the software, you get this lovely graph, intensity here on the vertical axis and wavelength on the horizontal axis. And you can actually see with your own eyes these lovely, deep, dark absorption lines. And of course, you can then do measurements on these absorption lines. They have a shape, and the shape of these lines also conveys a lot of information. And as I said, there's a lot of help out there. I mean, the BAA is very active in supporting spectroscopy, and I actually went on a whole weekend of learning about amateur spectroscopy a few years ago now, organized by the BAA. Had great fun, met some of the top amateurs in the country. This chap here, Robin Ledbetter, or Ledbeater, I should say. This chap here, Andy Wilson, he's actually one of the prime organizers of the spectroscopy side of the BAA, and many others. This chap here is the owner of Sheliak. And so I mentioned the support they give. So they have a mentoring scheme. So if you're a member of the BAA, people like myself, we're more than happy to sort of help you out, answer questions, and basically try and move you through that learning curve as best as possible. They even have spectroscopes that they loan. And once you become proficient at spectroscopy, you can upload your spectra to a database. And this actually is crucially important, not just as a source of spectra that maybe help you calibrate, if you like, your own progress, but as a science resource. And professionals use this database and others to take the spectra and use them in their own science papers. So once you're proficient, the information you're capturing is of scientific value without question. There are forums, online forums, to give you help. This is the RSpec forum, so the one, I suppose, really directly linked to the software I mentioned, Tom Field's software. And it's the forum most used by users of the Star Analyzer, the simple thread-on spectroscope. Also, there's a lot of discussion about using other spectroscopes and results, and there are 2 or 3 other forums as well doing similar things. So that's a bit about the technique and the background and the support. So just quickly touch on the origin of these lines. I love these. This quote: "There's no means by which we will ever be able to examine stars' chemical composition, mineralogical structure, or especially the nature of organisms that live on their surfaces." And this was Auguste Comte, the French philosopher, and he wrote this in 1833. And I love this. And this isn't my quote, actually. This is the quote of a member of the Wells and Mendip Astronomers who sort of shouted out when I was giving this talk to the Wells and Mendip Astronomers a few years ago now. Who shouted out, well, he was already wrong. Because, of course, Fraunhofer had observed lines in the sun spectrum in 1814, didn't yet understand their significance. But there was the way of actually learning about all these things that Auguste Comte said you couldn't. And so here's a brief kind of description of how that understanding came about. And I think it was this understanding that the laws of Kirchhoff's laws, developed in cooperation with the chemist Bunsen in 1860, that was really the motivation, the encouragement for the pioneers of spectroscopy to develop the technique in the 1860s. So people like William Huggins. I think it was this understanding that encouraged them to go out there, develop the technique, and learn about the starlight. So it's this idea that hot objects form a continuous spectrum. It's black body radiation, and that spectrum, the shape of that continuous spectrum, that rainbow, is determined by the temperature of that black body. Stars are approximately black bodies. They're really not quite, but in many ways they can be seen as black bodies. And so they produce this rainbow of light, and of course the stars have an atmosphere, if you like, a photosphere. So when the light passes through that outer layer of the star's surface, it interacts with the chemicals, the chemistry of that surface, and you get absorption. So that's the origin of these absorption lines. And of course, if you're not looking at that light directly through this cloud of gas, if you like, but you're looking to the side, you know, it's a bit like what goes up must come down. So the electrons in atoms that absorb light to produce absorption lines, they must cascade back down to their original energy, and they re-emit that light as emission lines. So this is the kind of situation where you'll see an emission line spectrum. So there's Kirchhoff and Bunsen. And this is the spectroscope they used. And of course, they were observing lines generated in an oven here. They put metals and various chemical elements in the oven, heated them up, and that heating process caused them to emit light in a very specific spectrum. And they broke the light up using multiple prisms, spread it out as much as possible, that blob of butter, and then observed the different emission lines that were produced in this telescope here. And they had a micrometer gauge, so they could, if you like, calibrate the position of those lines. And of course, what Kirchhoff understood was that an absorption spectrum, a fingerprint of a chemical in absorption, exactly matched the fingerprint of that chemical in emission. They were two sides of the same coin. So I love this quote. Warren de la Rue, a chemist, said, well, of course, now we have this understanding, the astronomer is going to be coming to the chemist for his understanding. I'm not sure that's still the case, but it was back then. I love that thought as a chemist myself. So if you take your star analyzer and just mount it in front of your digital camera, I mean, I've got a rather old one, a Fujifilm Fine Pix, and I went down to my local firework display in Shepton Mallet a few years ago, and I just, in a rather crude way, put the star analyzer here, mounted it in front of my camera lens, and I took some photos of fireworks. So these are the big fireworks that explode high in the sky, and this was a red one. So of course, you see this is the zero order image. So this is the light from the firework coming straight through the diffraction grating. So you get a beautiful in focus zero order image. And then cast to the right is the blazed first order image. So the really bright first order spectrum. And what's lovely about the huge sparks, as it were, that are formed from a big firework like this is if they're oriented just right, in this case vertically, then it's like light coming through a thin slit, isn't it? And so you get a beautiful spectrum. So this is the line of light that's producing this spectrum. And you can see that it's got bright lines in it, one or two here down in the violet area, but lots of lines in the red, and that's why this firework is red. And of course, what you're looking at here is the fingerprint in emission of strontium. This is the chemical element that's used in fireworks to make them red. So you're looking at the emission line spectrum of strontium. And Tom Field, this chap who wrote the RSpec software, he had the great idea of doing a periodic table of spectra. And I love that. And so here is the periodic table populated with the emission line spectra of all the chemical elements. So let's go back now, and we'll gradually creep back to astronomy. And this is where stuff gets, for me anyway, obviously really exciting and interesting. So if you break the starlight of certain stars into a spectrum, what you're looking at actually is the fingerprint of hydrogen in the starlight, the so-called Balmer series of absorption lines. So let's take a very famous constellation, the Plough, and we're going to look at the spectrum, as we saw before, of Alioth, which, of course, like a lot of stars, has an Arabic name. In this case, it means the fat tail of the sheep. And there's the spectrum that I showed you earlier. And you see in the spectrum this increasingly closely spaced series of dark absorption lines. Not much else. It's a pretty bare spectrum otherwise. And this is the concept. You have electrons at low energy levels around the atomic nucleus of hydrogen. It's just a proton. And then light is absorbed to jump to the next energy level. And obviously, as the electron jumps to a higher and higher level, more and more energy is absorbed. And if you tip the spectrum of Alioth on its side, you can essentially make these rungs of this ladder line up with our kind of concept of energy levels. Now, isn't that beautiful? So you're splitting the starlight of Alioth up, and you're looking at the atomic structure of hydrogen in starlight. So now we're ready to understand the sun spectrum. So here's the spectrum of the sun in red, running from the near UV to the near infrared. So this is taken with my ALPI spectroscope. And here I've put the emission line that's produced in what was then a really annoying sodium street lamp outside the house where I used to live up in Oak Hill in the Mendips. And you can see how the emission line from the street lamp exactly lines up with an absorption line here and here in the resynthesized spectrum in the sun. So this basically was the technique that Kirchhoff and Bunsen used in order to demonstrate without doubt that the sun spectrum showed there was sodium in the photosphere of the sun, in the sun's atmosphere. And that's the technique essentially that's used then to identify other lines in the sun. So we have iron, for example. These are just 3 of the darkest lines. There are many, many, many absorption lines of iron in the sun spectrum. Magnesium, this famous magnesium triplet, as it's called. Calcium, these are the 2 beautiful dark lines way down in the near UV, almost beyond the eye's vision if you were to observe this spectrum visually. And of course, people observe the sun in the calcium K wavelength, which I think is the shorter one here. Here's the Earth's atmosphere. And of course, you can't escape the Earth's atmosphere. We're looking at the sky through the atmosphere. And it produces very strong absorption lines from molecules in the Earth's atmosphere way out in the near infrared. So fortunately, they don't obscure the most interesting part of the spectrum here, but they definitely do start to play a role here. And of course, that's one of the reasons why the James Webb Space Telescope is in space, why many telescopes are in space, because there's intense activity, absorption of molecules in the Earth's atmosphere, particularly water, in the infrared. So if you want an infrared telescope, you really need to put it up in space. So some of you may be asking, well, what about hydrogen? I mean, look, I was sure that most of the sun's composition was hydrogen, and of course it is. It's got a very weak spectrum. There's that Balmer series that you saw beautifully painted in the spectrum of Alioth. Much, much weaker. What's going on there? Well, we'll touch on that. So let's really get out into space now. I love this quote from Huggins' essay. I soon became a little dissatisfied with the routine character of ordinary astronomical work. And it was just at this time that the news reached me of Kirchhoff's great discovery of the true nature and chemical composition of the sun from his interpretation of the Fraunhofer lines that we've just talked about. This news was to me like the coming upon a spring of water in a dry and thirsty land. Here at last presented itself the very order of work for which in an indefinite way I was looking, namely to extend his novel methods of research upon the sun to other heavenly bodies. So for him, the work of Kirchhoff and Bunsen was inspirational. And as I say, I think this is why astronomical spectroscopy, one of the reasons why it took off in the mid-1860s. So here's a photo of Huggins, a younger Huggins, I think probably the sort of age when he started his spectroscopic journey in the mid-1860s. And I say recreating the pioneering age of spectroscopy because Huggins made many fundamental discoveries very quickly using spectroscopy, and this is one of them. So here's an astrophoto I took of the Cat's Eye Nebula, one of the many planetary nebulae in the sky. I'll just zoom in a little bit. You can just about make some details. I mean, I was never a great astrophotographer, but I loved it and enjoyed it. And of course, by doing astrophotography, it was a bit of training to move into spectroscopy. So there's the nebula, and he pointed his spectroscope at this nebula. And at the time, there was a controversy about these sort of milky patches in the sky. You know, were they very distant clumps of stars, or were they hot gas? And of course, the spectroscope can answer that question. You know, if there's a clump of stars, then starlight, as you've seen, produces black body radiation across the whole wavelength range as a kind of rainbow. So I put my spectroscope, ALPI, on this nebula, and this is the spectrum I got. So remember, the violet blue is at this end, the red is at this end. There's no rainbow at all. There are just emission lines. So Huggins saw exactly this visually in his spectroscope, and he wrote in August 1864, the light of the nebula was monochromatic. So in other words, just these bright lines. And so unlike any other light I had yet subjected to prismatic examination, the riddle of the nebulae was solved. The answer, which had come to us in the light itself, read, not an aggregation of stars, but a luminous gas. So he'd solved this controversy at a stroke. No debate. This was a patch of gas illuminated by a very hot central star we now know is a white dwarf. And planetary nebulae are, if you like, the final death throes of a star, probably similar in mass to the sun, which has cast off its outer layers of gas and exposed the core, the residual core, which is the white dwarf. So let's reduce the universe to chemistry, which I like doing as a chemist. And this is the composition of the universe, pretty much set the same on average in all directions. You know, 93% hydrogen, 7% helium, and everything else is tiny also-rans. So think of the spectrum of the sun that I showed you and that Fraunhofer drew. How can traces of calcium, 2 parts per million in the sun's atmosphere, more or less, produce such an intense double pair of absorption lines, if you remember, way down there in the near UV? You know, what's going on? Well, here's how the rainbow is formed. You know, we talked about stars being black bodies. So cool stars are shaped like this. So the light peaks way out here in the infrared and near infrared. So these stars, I mean, Antares that I mentioned, Chris, at the beginning, that's probably something like 3000 Kelvin is its surface temperature. The sun is more like 5,500, so it's got a spectrum, a rainbow, a bit like this. And then, well, stars like Alioth, they are actually much hotter even than 7,000. So they're peaking way out here in the UV. So notice how the shape, the color of the spectrum changes as the temperature increases, but also the intensity. You know, hot stars produce masses more light than cool stars. So here is a series of spectra that I've organized by classification. So this kind of classification was understood from spectra as early as the late 19th century. And it was understood that you had to order stars by temperature. And if you take their spectra, like I have done, and I've ordered them by temperature, you start to see a curious thing. So here, for example, is one of the absorption lines of hydrogen. It's quite faint up here in the hottest O-type stars. Then it starts to get really dark in the A-type stars, and this is stars like Alioth. And then it starts to fade away again. And this is very typical. So metals, for example, they don't actually appear in spectra until the stars get quite cool. So there's calcium, there's iron, or one of the iron lines. There are many, many of them. There's sodium. Helium. Now that only appears faintly and only in the hottest stars. Completely disappears in cooler stars. And there's hydrogen. You know, I mentioned the way it sort of starts faint, becomes strong, and then becomes faint again. And here's the atmospheric lines. Now, they don't line up very well. Some of these spectra are quite old, and I was still developing my calibration technique. It's quite difficult to calibrate, in other words, to set the position of the wavelength right down at this far red end. And it takes a bit of experience and practice. I wasn't so good at it back then. But anyway, they should all line up. And here are those same spectra, but graphically. So you can see visually in the graph how the hottest O-type stars, this pink line here, they peak way out here in the near UV, and then gradually that peak moves and moves and moves and shifts towards the near infrared as the stars cool. I think that's, I love seeing graphs, as I said, and I actually think that's a beautiful way of presenting spectra, just as beautiful as the visual spectra themselves. And here's the woman who helped us understand how it could be that 93% of the composition of a star is hydrogen, and yet only at certain temperatures is that spectrum readily visible. And she did this in a PhD thesis in 1925, and it was described by Otto Struve, one of the famous observers of binary stars. Undoubtedly the most brilliant PhD thesis ever written in astronomy. Did she get the credit for it? No, her supervisor did. You know, and if the Nobel Prize had been around back in 1925, she would surely have won it. And this is graphically essentially what she understood, which was that the strength, that's this vertical axis, the strength of the absorption by chemical elements depends on the temperature. So this is this plot of temperature versus line strength for different chemical elements. So it's essentially doing what I just showed you visually in the set of my spectra that I presented in order of temperature. So you can see helium really only appears and then disappears in the hottest stars, the B and O type stars. Hydrogen peaks in strength in the sort of mid-temperature stars, A-type stars like Vega and Alioth. The sun is around here, so you can begin to see why the sun has such intense calcium lines and quite weak hydrogen lines. And then right down here at the cool end, you're beginning to be cool enough for molecules to form in the star's atmosphere. So I used that technique, for example, and I wrote this paper in the variable star section circular for the BAA. I used the technique of measuring the strength of absorption lines to monitor the change in brightness, if you like, of Cepheid variable stars. Now, I have, unfortunately, obscured the, so I'm going to, whoops. I just reshare my screen again. Don't know why that stopped sharing. Bear with me. I'm just going to remove that so you can actually see the graphs that I plotted. So here they are, two Cepheid variable stars. So these are the stars that are used as distance ladders, distance indicators, because their brightness is proportional to their the period, the rate at which they vary. So the blue dots are the visual magnitude of the star. So you get this classic Cepheid variable shape, and my orange dots are my measurement of the temperature of the surface of the Cepheid variable. And you can see how the two very closely correlate. So it's just a different technique, a spectroscopic technique for measuring the variation in brightness of Cepheid variables. So going back to my reduction of the university chemistry, what about molecules, which I mentioned, you know, and I kind of ask this question, well, surely it's too hot for molecules to form in the atmospheres of stars. Well, Angelo Secchi, one of the other pioneers of Huggins at the same, of spectroscopy at the same time as William Huggins, he was the first to take the spectrum of cool stars. And this one is the beautiful binary star, the brighter component, Razel Gethi, which is the brightest star in Hercules. Look at that. I mean, that's just such a, for me anyway, such a stunningly beautiful spectrum. I mean, it gets brighter out in the red, near infrared, because this is a cool star. But because it's cool, titanium oxide is able to form in the atmosphere, and that produces, like lots of molecules do, it produces these beautiful bands, these absorption bands. And that's very characteristic of molecules. They don't produce just individual lines, they produce very dense clumps of lines arranged in bands like this. So he described these banded spectra for the first time. He didn't understand the origin, but he described this kind of spectra as a very specific class of spectra. But you don't have to find molecules in stars. You can go hunting for them in comets. And this is my spectrum of until a comet Neowise a year or two ago. This was the brightest comet we'd had in the Northern Hemisphere for some time, Lovejoy in 2015. And I took its spectrum, and here it is. Here's its spectrum. And you can see it's full of bands, but this time they're emission line bands. They're not absorption lines. And this is because the coma, the gas around the comet, is fluorescing in sunlight. And it fluoresces depending on the chemistry in that gas, and that's the chemistry of carbon. So you see these emission lines of carbon molecules, basically. And just to add an extra dimension to make it more real, I also took the spectrum of my gas hob flame, and it exactly matches pretty much the spectrum of the comet. Isn't that beautiful? So you're looking at carbon chemistry in the halo, the atmospheres of comets, which is very suggestive, isn't it, of the origin of biologically interesting molecules. And what about motion and change? Well, here's Huggins again. He was the first to understand the significance of Doppler shifts and its potential application, not to the change in frequency of sound, like when an ambulance comes towards you, but the change in frequency and wavelength of light, depending on whether the body is moving towards us, blue shifted light, or away from us, red shifted light. And he was the first to attempt in 1868 to measure Doppler shift. He thought he could see it in Sirius. It has a very tiny motion. So I'm not sure if what he saw was real, but he was looking for it. That's the critical thing. So what I did was I measured the Doppler shift of a star that really is moving very fast towards us. And that's Barnard's star, which is actually the nearest star to us from the northern hemisphere. It's about 6 light years away. Very faint star because it's a very cool star. There's its spectrum. And this is a little video, so I can't slow it down, I'm afraid. So what you're going to see is just sort of absorb it as it goes through. So here's a plot first of some astrophotographs. Can you see Barnard's star? Here it is. And I took one photo every year at more or less the same time of year, and you can actually see it moving across our line of sight really quite fast. But with the spectroscope, I can show that it's moving towards us as well. So here's its spectrum, and there it's very strong absorption of sodium. And if I match that to the emission line from a sodium street lamp, can you see how the absorption is just to the blue side of the emission line from the sodium street lamp? So it's blue shifted. And if you actually measure the position of that absorption line compared to the emission line, it's blue shifted by about 100 or 150 kilometers per second. So astrophotography tells us there's a component of motion across our line of sight. That's what's called the proper motion of the star. And spectroscopy, using an amateur spectroscope, tells us about its motion also towards us. So it's kind of moving obliquely, if you like, across us, Barnard's star. So an interesting star. Just let that run once more. So there's the spectrum out of the camera. I process it to turn it into a graph, look at the position of the sodium absorption line, compare it to the position of a stationary sodium emission line, and you can work out the Doppler shift. And you can do that with galaxies too. And of course, here's one of the first astrophotographs ever made by Sir Isaac Roberts in 1886. And this was of the Andromeda galaxy, which of course is our nearest neighboring grand design galaxy, very bright in the sky. You can see it in telescopes. And he took this beautiful photograph. Now, this is the other portrait I mentioned to you. So on one side of the doorway was William Huggins. On the other side was Margaret Huggins, his wife. And she didn't just sort of help him in his studies. She was actually what I would call a collaborator, particularly on the photography side. She helped him develop photography as a technique in spectroscopy. And when she saw this photo from Sir Isaac Roberts, she wrote this: "Mr. Roberts' work gives the body. If we can get good spectra, we should have the soul." And I absolutely love that. So it's just, again, this idea that packaged up in this light is so much information if you can use spectroscopy to get at it. Now, unfortunately, the photographic techniques that she had at her disposal weren't sensitive enough to capture the faint light, even from a bright galaxy like Andromeda. But my CCD camera can. So there's, if you like, one raw image out of my camera. These emission lines, by the way, they're not there in the spectrum of Andromeda. That's light pollution, polluting the photograph. The great thing, actually, is a little aside about spectroscopy, is you don't have to worry about light pollution because you can just subtract it when you process the spectrum in the software. So you remove the light pollution from your image. So you can do spectroscopy from light polluted areas without problem. And if I then turn that into a graph, this is the graph form of that spectrum. And you can see this is an oxygen absorption line from the Earth's atmosphere, and it's pretty much bang on where it should be. And you'd expect that. The atmosphere is stationary relative to my telescope. But look at the absorption lines of some of the absorption lines in the spectrum of the core of Andromeda. And they're actually blue shifted, aren't they? Compared to this green line here, which is where they should be if the element producing them was stationary. And when you work out the numbers, you get to a speed towards us of about 400 kilometers per second. So blue shift of 400 kilometers per second. The actual value is about 300. I thought that wasn't bad, really, for an amateur spectroscope. And of course, you probably know NASA modeling predicts that Andromeda will collide with the Milky Way in a few billion years' time. You can also measure the speed of rotation of a binary star. This is Cheliac, which actually gave its name to the company that made my spectroscope. That's the star here. It's actually a binary star. Its spectrum is here. It's a hot star. You can see it peaking way off into the blue. And it's got emission lines here. And that's because the absorption lines in the spectrum come from one of the two stars. The emission lines come from the other one. So if you capture spectra on different nights, you can actually see the change in Doppler shift of these absorption and emission lines. So here's the spectrum I took on one night, and here's the spectrum I took on another night. And I'm focusing in on this position here. Can you see how the absorption is to the right, to the red side of the absorption here, and here the emission is to the blue side of the absorption. So you're seeing literally the lines flip either side as the two stars orbit each other in our line of sight. And if you don't believe me, then it is possible for professional telescopes to separate these two stars. And this is the result. So this is a real video of a professional sort of observation of these two stars. And there they go. But I can see this using my spectroscope. You can even do that on supernovae. You can take the spectra of supernovae and show that the explosion is expanding at 15,000 kilometers per second. And you can watch binary stars. This was a 5-year-long project that I did. And what I was watching for, you see that tiny hot blue star? Every 20 years, it goes behind the red supergiant. So this is a video I created in a bit of software that's available free online. These two stars, they're both massive stars, so they will both die in spectacular supernovae, but one is slightly further ahead in its evolution, the big red supergiant. And actually, the size of that, its hot blue companion, it should be almost invisible. I've exaggerated the size of that blue star compared to the red supergiant. And here's just an animation of 3 of the spectra I captured. And basically, as that hot blue star disappears behind the red supergiant, it carries its emission lines with it, and they disappear. So you can see them beginning to fade in that video. So I spent 5 years, along with a few other amateur astronomers, following this star. And if you plot the intensity of the emission lines on the left against date, you get a beautiful image picture of the eclipse. So this is one of the emission lines. It actually falls to 0. This is another one. It doesn't completely disappear because the gas producing it actually extends further than the size of the supergiant. But you basically get a picture of the eclipse. You can measure its center point, so you can get the period of the eclipse. And I wrote a paper for the BAA journal, which appeared, I think it was last August's journal, about this eclipse and the project and the results. And there were some very interesting results. And in fact, I'm going to give a talk about this at a BAA meeting in London in May. And you can also look at exploding stars, novae. I mean, there were 3 bright novae actually last year. One of them was Nova Cassiopeia. I don't know how many of you observed this in your telescope, but it actually reached a peak magnitude of 5.4, so almost naked eye in a very dark sky. So this is an astrophotograph and showing the nova just here. Actually, it was very near the Bubble Nebula and one of the Messier open clusters. So it made a beautiful astrophotograph. And actually, this was a photograph taken by another Wells and Mendip Astronomers member just before the nova explosion. So I've kind of pointed to the spot, and you can see there's nothing there. Well, there is actually a faint star there, but it's only 16th or 17th magnitude. And then that star exploded as a nova. And I followed this nova in my spectroscope. And it makes actually a beautiful object to follow. I've taken now about 40 spectra of this star. And you can see how amazingly it changes with time as this explosion evolves. In fact, the emission line here, this is the hydrogen alpha emission line, becomes so intense that if you plot the relative intensity up to the point of maximum brightness of this line, you don't see anything of what's going on down here. So I'm going to crop that y-axis a bit, and then you can see the change a bit better. And you can see how much is going on in the spectrum, how the explosion is changing, how different chemical elements are being expressed. You can measure Doppler shifts, so you can measure explosion velocity. It really is a fascinating project. And here are the spectra just plotted one on top of the other. So you can almost see visually how, you know, here there's nothing in this area at the beginning of the explosion. And as we move forward through time, suddenly you get a whole host of lines formed around here. These are iron, and then they disappear again, then they reappear, then they disappear again. And then there's a line here. This is helium that is quite strong at first, then disappears, and then reappears and becomes very intense now up here. So there's loads going on here, and they really are beautiful and complex objects. So look, I know I've been talking for a bit over an hour now, but I'm nearly done. Just want to touch on the search for life. Now, I'm not pretending that we can search for life down here, but here's William Huggins again. He wrote in 1860, and he didn't pretend to be able to find life with a spectroscope, but his knowledge of the spectra of stars caused him to think this: the differences which exist between the stars are not differences of the higher order of distinct plans of structure. There is therefore a probability that these stars are, like our sun, surrounded by planets, adapted to be the abode of living organisms. What an amazing statement to make back then. But he made it because he saw not just the differences between spectra of different stars, but he also saw their similarities, that there were the same chemical elements in all these different stars. So he kind of extended the reasoning to say, well, maybe they all have planets as a result. So, and how right he was. So there are two opportunities to use a spectroscope to look at the atmospheres of other planets, of exoplanets. You can look at them here in reflected light. So as they move behind the star, they're reflecting more and more of their light. So maybe you can pick that up in the star spectrum. And of course, if you're lucky, the orbit of the planet is in our line of sight, more or less. So the planet will actually pass in front of the star. So the starlight then comes through the atmosphere. And maybe there's a chance there of looking at what's in the atmosphere. And I can do that with solar system planets with my spectroscope. So let's start with that situation where the planet is reflecting starlight, in this case sunlight. And of course, you know, that's how we see planets in the sky. We see them because they reflect sunlight. So of course, if you take the spectrum of the sun here and compare it to the spectrum of the moon, which I've done here, these are just a couple of astrophotos I took a few years ago of these two, the spectrum is identical. So moonlight is definitely reflected sunlight. There's no atmosphere on the moon. The sunlight is unaffected by being reflected off the moon's surface. However, if I point my spectroscope at Saturn and I cleverly try and orient the slit, which is here, so this is out of the guide camera, you see I've put the slit lengthways, if you like, along the planet. So I catch the planet here in the middle, the gap between the planet and the rings, and then the two ring parts either side. This, by the way, is just an image without the slit going across the picture, just so you can see what it looked like in my guide camera. And this is the spectrum that's cast as a result. And you can see the spectrum of the rings, actually, take my word for it, it's the spectrum of reflected sunlight, like the moon. Here's the spectrum of the planet. And can you see how there's definitely something here that is not in the spectrum of the two rings? And certainly here, there's a massive area of black absorption bands. So we're talking molecules. Let's zoom in a little bit here. So you can see here. So the spectrum of the planet is absorbing here. And this actually is one of the characteristic absorption bands of methane. This here is one of, much fainter, but it's there, is one of the characteristic absorption bands of ammonia. So using my spectroscope, I can look at the chemistry in the upper atmosphere of Saturn. And you can do this with Jupiter, you can do it with Uranus, you can do it with Neptune, and you see these really dramatic absorption bands of ammonia and methane in particular. What about the other situation where the planet is passing in front of the star? Well, you might say, well, surely we can't do that here. When you're right, we can't. But what we can do, there is one situation where you can look at the atmosphere of a planet in that way. And that's when you have a total lunar eclipse, because sunlight is being passed through a long path through the Earth's atmosphere and then onto the surface of the moon. And so if you've ever seen a total lunar eclipse, you get this beautiful orange-red moon. And that's because the sunlight has passed through this huge length of atmosphere. It's like looking at a red sunset all the way around the rim of the Earth. So the last beautiful lunar eclipse we had was in 2015. And I don't know how many of you saw this eclipse. It was magical. I think the weather across most of the country was very good. Certainly here in Somerset, it was 3 a.m. I was out there, nobody else was. And I watched the sky turn from this almost starless sky that you get with a bright full moon. And as the moon's shadow passed, as the Earth's shadow passed across the surface of the sun, suddenly, across the surface of the moon, suddenly the color of the moon turned obviously a very much fainter orangey red. All the stars came out. So you had a full moon in a faint orange red surrounded by all the stars as if it was a beautiful dark night. My purpose, of course, was to take the spectrum of that beautiful red light. And this is it. This is the view I had in my guide camera, by the way. So I put the slit across Tycho crater, which is one of the brightest parts of the moon. And this is the spectrum I got. Obviously, it's a bit distorted in shape in terms of peaking in the red end, and that's because the light was reddened by the sort of sunset effect. What I draw your attention to is this huge scoop taken out of the spectrum, and this is what's called the Chapuis band of ozone. So it's an absorption band of ozone. You don't see it looking straight up through the atmosphere. The ozone layer is very thin, but you do see it if the light has come through, has slanted through such a long path through the atmosphere as you get with a total lunar eclipse. And so this is the one opportunity to see the Earth's atmosphere as if it was an exoplanet. And ozone produces an amazingly intense absorption spectrum. So a few years ago, I went to one of the first Caroline Herschel Prize lectures at Bath University. So this is a prize basically founded by the Herschel Society in Bath. And it encourages female astronomers early in their careers. So this academic came to talk to us about the search for life using spectroscopy and how biosignatures are basically signatures of molecules that are sort of chemically exclusive. They would normally react with each other. So if they are present together in an atmosphere, they must be being regenerated. And of course, methane, for example, one of the critical sources of regeneration is biological activity. And then she went on to talk about the huge telescopes that are being built. This here is the James Webb telescope mirror here, and it's the sensitivity and the infrared activity, because molecular absorption and emission is most strong in the infrared. It's this kind of capability that will allow them to look at the spectra of exoplanets and pick out potentially the molecular signatures of life. So when James Webb gets up there and starts doing science, it may be that it will make a discovery in the atmosphere of an exoplanet that's highly suggestive of the presence of life. So I'm near the end of my talk now. So I like this. So, you know, with that in mind, do you think somewhere out there aliens are measuring our atmospheric chemical composition through absorption spectroscopy? So my last slide, what does spectroscopy mean to you? So have I changed your thinking? Well, I hope I've shown you it's a unique observing method. You can see things with a spectroscope that you can't see visually or photographically in amateur telescopes. You can do all sorts of science and detective work, as I think I've shown you. And really, I think it is beautiful, just the appearance and the understanding of the information that spectra can carry. And thanks for listening.
Wow. Thank you very much, Hugh. Can you hear me?
I can hear you, yeah.
That was wonderful. If you'd like to stop sharing for a moment, but we might ask you to share again to go back to slides on any questions. But yeah, that was wonderful. Thank you very much indeed. We'll give you a generous round of applause at the end. It'll be a virtual.
Virtual. That's very nice. Good.
Well, you're getting it now. Actually, let's do it now. Everyone's doing it now. So here we go. A virtual round of applause, first of all. Thank you very, very much. We really, really appreciated that. Lots of thumbs up. Yeah, fabulous. For someone who came into it relatively late, obviously your chemical background has stood you in good stead.
Yeah.
And perhaps the good lead-in as well was the general interest in astronomy and the photography side. And I suppose the two, you know, are kindred spirits, and they kind of naturally come together for you.
Yeah.
even so, I'm pretty impressed. I understood most of it. Some of the, you know, I love the bullet points in. Was it angstroms? You were using angstrom signs for each bullet point.
Yes,
I got that. Yes, I got
right.
that. That was a good touch. I like that. Okay, well, as ever, I'm going to hand over to the floor, and I hope we have some astrophotographers with us. I'm not sure how many spectroscopists we have, if that's the right word, but I'd be interested to hear what people have to say about that. So I'm going to hand over to the floor. Please put your mics back on and your cameras, if you wish, to show your face. And have we got any questions?
Yeah, I mean, I mean, just to say, whilst perhaps people give it some thought, you know, you mentioned astrophotography, and some of your members do astrophotography, and there's no question that if you already do astrophotography, that's already a significant shortening and lessening of the learning curve, because the starting point for spectroscopy is capturing the images of these spectra, and they're very faint, so you do have to use the right techniques, the right cameras. Yeah, so astrophotography is definitely a good starting point, a sort of you know, leaping point for spectroscopy, definitely.
Oh. Well, yeah, please go ahead.
Well, I wanted to say how great that talk was. It took us from, and the historical aspects are really great too, that sort of slowly building up to what it's all about. And you're right, there's not much done and said about it. My husband was into, well, he was a geochemist, and he really enjoyed that part of astronomy.
Yeah.
Having said that, we never actually got going with spectroscopy, or I hate to say, for the photography, because of work and various other commitments.
Yeah.
But I appreciate your talk. It was really, really good. And
thank you.
You know, if you do come again, I'm quite happy to put you up. I'm not too far away from Hereford, and I'd be delighted to put you up if you wanted to come again.
That's very kind. So, thank you.
Well, there's an offer for you, Hugh.
Okay.
Just going back to the early days then, has anyone got a question immediately now? I don't want to hog the questions.
I just perhaps one quick question, if
please,
I might, Chris. Brilliant talk, Hugh. Thank you very much. Enjoyed it enormously. As a sort of an astrophotographer type person, I was interested in sensitivities, i.e. how dim can a star be before you can't measure it anymore because it just takes too long?
Yeah, a very good question. Obviously, it depends on a lot of things. The telescope, for a start itself, the aperture, the nature of the telescope.
Oh, of course.
The camera, the and so on. But for me, for example, I think if you had perfect guiding, auto guiding, I know amateurs who are using the same spectroscope as me with a similar telescope, and I use an 8-inch Meade Schmidt-Cassegrain reflecting telescope. They could probably capture spectra down to, with a standard LP, maybe down to magnitude 14, something like that. I can probably realistically not go any fainter than about magnitude 11, 10 or 11th magnitude. And then if you use a star analyzer, which, you know, this slitless spectroscope, because there's no slit, the slit itself, it loses light. You know, the size of the star maybe is slightly bigger than the 23 micron width of the slit, so you're losing light over the edges of the slit, and just the technique itself of slit and diffraction grating, you lose light. So but the star analyzer allows you actually to go even fainter because there's no slit. There are no losses because of that. So that quasar that I showed you the spectrum of, you know, I couldn't do that with my LP, but I can easily do it with the star analyzer. So, you know, it varies depending on the equipment you have and what you're using. But that's a kind of idea that, you know, getting much beyond sort of 14th, 15th magnitude is difficult, quite difficult.
Brilliant, thank you. It just gives me a perspective of, you know, sort of what you could use the spectroscopy for in terms of the, you know, the targets you could go after and the measurements you could make. Fantastic, thank you.
Yeah, but there's compliments on your Horsehead Nebula there, by the way, Rob. It's beautiful.
Well, thank you very much.
Yeah,
that is actually his, Hugh, as well.
Yeah, no, amazing.
Yeah. I think that was about 10,000 seconds worth of exposure to get that.
I bet. Yeah, worth it though. Worth it.
Oh, thank you very much.
With that kind of equipment, you can't see any fine detail like related to magnetic effects, like Zeeman effects or anything like that.
No, I think Zeeman effect is beyond the resolution. I mean, people do solar spectroscopy, and obviously the sun being incredibly bright, there's plenty of light, so you can use extremely high resolution spectroscopes to observe the sun. And high resolution means spreading the spectrum wider and wider. So if you like, you pull the lines apart, but of course you get fainter and fainter. So actually people do very high resolution spectroscopy on objects like the sun, where probably you can pick out, you know, these very small wavelength changes due to magnetic effects. People actually create images of the sun, you know, using a spectroscope, because, you know, logically, if you think about it, what you're producing is like a line image in wavelength, using a slit. So they just build an image of the sun from these lines of light all stacked together, and that's called I think it's called a spectroheliogram, the output. So it's if you like, it's a two-dimensional picture of the sun that someone would normally capture through an hydrogen alpha telescope, but they capture it in hydrogen alpha lines from a spectrum. I'm probably not explaining it very well, but I've seen people do it. It's becoming quite popular, actually. So it's a different way of creating this picture of the sun in specific wavelengths. But of course, you know, it sidesteps the problem of having to buy a different filter for each wavelength. You can actually observe the sun in whichever wavelength you like, because your spectroscope is splitting the sun into all its different wavelengths. You just pick one of them. So
cool.
Hugh, is there any purpose in looking at the sun spectrum in some kind of way as a kind of base datum, as a kind of default spectrum against which we can measure other spectra from other stars and make some kind of deduction or comparison? Or is the sun, it's just a basic G-type star, but there's no purpose to say it's a base spectrum because it's just a star?
I mean, that is an interesting question, Chris, but do you mind if I answer it in a slightly oblique way, because it touches on an important part.
You make a good politician.
Well, okay, but at least I'm admitting it.
Yes, true.
It's an important part of spectroscopy, which again people can feel frustrated about, but they shouldn't. I kind of liken it to supermarket economics. You know, you go into a supermarket, well, you used to, it's less common now, and you go and get two for the price of one. You know, and you feel that's great. What a bargain. Unfortunately, spectroscopy is the other way around. You get one for the price of two. So you generally have to take the spectrum of two stars in order to get a good science quality spectrum of just one of them. And that's because every time you take the spectrum of your target, this interesting object you're desperately excited to find out about, you need some way of just what you're saying, of calibrating that spectrum. And one of the ways, critical ways of doing that, is to take the spectrum of a very nearby reference star, and there's a catalogue of reference stars, and then you use that reference star spectrum to calibrate the shape, if you like, of the target star. In other words, you know, is it a hot star, a cool star, or whatever. You can also use it to calibrate the wavelength, and that's a critical thing that you do in the software. One of the things that spectroscopic software does is put that x-axis calibration to your spectrum, to the image that you've taken in your camera. So you use your reference star to calibrate the position of the lines in your camera image. I actually have a lamp that's part of the Alpi spectroscope. That, if you remember it in the picture of the scope attached to the back of my telescope, there was a white box. That white box contains a neon argon lamp, and this mixture of neon and argon produces a whole slew of emission lines at obviously very precise wavelengths, running from the near UV to the near infrared. So every time I take the spectrum of a star, at the end of my kind of project, I switch on that lamp and I take the spectrum of the lamp, and then that automatically allows me to calibrate where on the camera image is each wavelength. And you have to do that each time you go out, because every time you take your spectroscope out and put it on the back of your telescope, the position of the spectrum on the camera sensor is actually slightly different. You can't avoid that. So that's why this idea of calibration is really important. But it's like all these techniques, that beautiful image that you showed, Rob, behind you of the Horsehead Nebula, that isn't a product of a week's experience in astrophotography, is it? That's the product of years of experience, I'm sure, because there are so many steps to astrophotography and to spectroscopy. And to get a really good quality spectrum at the end, you need to get all of the steps sort of just right. And that does, it takes learning, but it's fun just going through the learning process. But anyway, your question, can the sun be used as a reference star? Surely it can in certain situations, but I just answer it more generally. You always take the spectrum of a reference star when you do a night's observing.
Okay.
Can I ask please, how exactly do you focus on the spectrum? You showed us the difference between the Bassanov mask and the star focus and the spectrum focus. Based on that curve. Do you have that curve available in real time as you do it?
Well, you do really, because your camera is picking up registering the spectrum all the time. So you can actually, I basically have two screens on open on my laptop. One is the guide camera view, so I know where I'm putting the objects on the camera, and the other is the science camera view. So you can adjust the focus of your telescope until the science camera view, the lines appear darkest and narrowest, if you like. So yeah, in real time, you can adjust the focus. Although, to be honest, I don't do so much observing now with the star analyzer as I used to. But I kind of learnt what the Bassanov mask pattern should look like for the spectrum to be in focus. And so at the beginning of every night's observing with a star analyzer, I would just put the Bassanov mask on the front of the telescope, and I would turn the focus until the Bassanov mask image in my science camera looked as it should. And then I knew that the spectrum was in focus, and then I could just carry on and capture whichever object I liked, and it would be in focus.
Thanks very much indeed. That's really fascinating.
So, but it's kind of linked, isn't it, again, to just learning the technique, and it can appear frustrating. And I honestly know many people who, they buy a star analyzer because I guess that's sensible. That's £100. And if you really, really don't get on with spectroscopy, you've only spent 100 rather than 1,800. I actually bought an Alpi straight away because I knew I would not be putting it to one side. But it can be frustrating. And actually, although it looks more complicated, it is actually easier to use a slit spectroscope like the Alpi than it is to use a slitless spectroscope like the simple star analyzer. So, and people can get frustrated pretty quickly, and I can understand that. And, many people fall by the wayside who start spectroscopy, which is a shame, but it is just the reality.
Would you recommend the book from Shellyak? I think it's called Starting in Astronomical and Spectroscopy or something like that. I understand. Yeah,
I absolutely would, Gordon. I would absolutely recommend it. I think it's beautifully written, but also technically written. So it gives you an understanding of the technique and the kind of science behind it. But it's also, I found, very motivational in the way it's written. So yeah, definitely recommend that book. Absolutely.
Right, thanks.
Introduce amateur spectroscopy, but I find in much more of a sort of rote way. They're good, but that book, yeah, absolutely, I would recommend
it. Anybody else? If not, I've got one more quick one, just on a historical note, Hugh. I thought that Fraunhofer lines was kind of a catch-all, an alternative name for spectral lines, but I think you said something that it was for particular lines, particular emission lines, which are always absorption. I'm not sure which.
Absorption lines, yeah.
Not the entire spectrum. I thought Fraunhofer was more renowned. Was he German? I think he was German. Was he?
Yep, yeah, he was.
Just as the Germans called X-rays Röntgen rays, we call them X-rays, but we seem to have an aversion to acknowledging anyone who isn't British, who's invented something or discovered something. But but Fraunhofer, it seems to me, gets a bit of a bad rap, really, because we know that Newton had the prism, but he really failed to look deeply into it. He didn't really seem quite to understand the significance of what he was looking at. Famously, your neighbour William Herschel of some time ago accidentally discovered infrared, I think. Indeed. When he was projecting a spectrum on the table, and the famous thermometer thing. Fraunhofer did all this work, but it seems to me he gets a bit of a bad rap. Would you agree? Or
well, yeah, I don't know if he gets a bad rap, but as you say, his name is now assigned to the darkest absorption lines in the sun spectrum. So it's a way, if you like, of acknowledging his discovery of those lines. I mean, he discovered 500 roughly lines, but it's the darkest ones that sort of carry his name, the Fraunhofer lines. And yeah, I mean, I think he was just a man ahead of his time, really. So the observation and the exquisite nature of the observation far surpassed the understanding. Yeah, so in that sense, his discovery kind of, in an astronomical way, just lay at one side for 50 years, really. 50 years. So yeah, does he get a bad rap? Yeah, I don't know, but certainly his name is there. It's immortalized, Fraunhofer lines, and they're specifically the solar lines. So they may be related, obviously, to similar lines in other stars, but essentially, if we're talking about the Fraunhofer lines, we're talking about the solar absorption lines specifically. Yeah.
Okay, thank you. Well, I think talking raps, I think that is a rap.
That is a rap.
Has anybody got a final comment before we offer our thanks again? No? Okay, well, Hugh, let's give you another round of virtual applause.
Oh, thank you, Chris.
And thank you very, very much indeed. It really was beautifully presented, beautifully illustrated. That's the thing about spectroscopy. It's very pretty as well, isn't it?
It is very pretty, and I'm glad you feel that, Chris, because I agree.
Lots of colours, which we all enjoy.
Yeah.
All right. Well, thank you once again, Hugh. In every respect, I really do appreciate the time that you've put in. And
no problem.
Thank you very much. And I hope we can invite you back again for something similar or something different. I'm sure you have other interests and other things you could talk to us about.
Absolutely.
Obviously, but...
I do. I mean, I'm a great fan of binary stars.
Right.
Look, you cannot expect me to do any talk without some spectroscopy in it.
That's okay. That's fine.
But certainly, I love talking about binary stars. So that's a talk that I love to give as well. So,
okay.
Yeah.
Well, we're booked up to the end of our season, but next year we're starting to look at things. So you never know. If not, then the season after it. I'm sure you'll still be around, and I shall be in touch. But in the meantime, thank you very, very much indeed.
Great.
Okay.
Yeah, nice to meet everybody. Bye-bye. Right,
everybody, I'm going to close unless anyone has anything else to say on, internally. No, we're all done. Okay, until next time. And hopefully we're going to get one more observing session in. Numbers were a bit low this time, but people had legitimate reasons for not being able to make it. Let's hope for clear skies. And next time we've got Bob Misen with famous comets in history. So until then, all the best, everyone. And thanks once again, Hugh.
Bye.
Bye-bye.